Alright, now let's do a game which consists of discussing the exercise 5 and 6 on section 15.2. But I like to do a little bit more than simply compute the integral, because computing the integral is an easy thing. What I like to do is to recognize the region of integration when I consider an iterated integral. Alright, here what is this integral? So you integrate first with respect to y from 0, that's an x here. You integrate first with respect to y this integrand from 0 to x squared, and then once you have done this, you got of course a result that depends only upon x, and you integrate the resulting integral from 0 to 1 with respect to x. What is this region? So the region says x is bounded by 0 and 1. Okay. This is x equals 0, and this is x equals 1. Now, once we fix x in between, the bounds for y vary between 0, so y equals 0, so that's in other words the lower graph, and y equals x squared, so this is something like this. And the region under consideration is also, of course, this one. That's important to know where what is this guy telling you. Now, can I interchange the order of integration instead of integrating first with respect to y and then with respect to x, which, to be honest with you here in this case, it's the best idea, but we could at least express this integral, the same iterated integral, by inverting the order of things. Now that we know which region we are talking about, yes, I can probably say that this integral here, so I need to give names. Let's call it capital A, and this one is going to be called capital B. I'm going to discuss those two cases, guys. Alright, so I can express the integral A like this. The bounds, I can eventually integrate with respect to y. I need to know what is this point. So this point is the intersection of the line y equals x squared with the vertical x equals 1. So of course y has to be equal to 1 here as well. Just because when x equals 1, y is equal to 1. So the bounds for y is clearly 1 and 0. And I integrate again dy. Now the integrand will be definitively the same, that's nothing has changed. But the bounds for x will be very different in that case. When I choose y between 0 and 1, this is my y, you see somewhere here. What are the bounds for x? You see the lower bound for x is not what we think it was, it's not 0, it's actually this quantity. So it tells me that y equals x squared is certainly a graph of x, but it also can be seen for the region under consideration as a graph of x over y. If nothing else, then say that x equals the square root of y. So the lower bound for the integration will be square root of y, and the upper part will be y equals 1. Now, for this example, is it really wise to do this? The answer is definitively not. Why? Because finding out an entire derivative of cosinus x third, this is a very tough request. Actually, to be honest with you, I don't know how to compute an entire derivative of cosinus x third. So that integral, if I want to be very nasty, I can give you in a quiz. It will be very cruel from me. Obviously, I will never do that. I will definitively never do that. You would have a hard time to compute this integral unless you use a numerical method and whatnot. But that's another story. But remember, you had the option of flipping the integral, and actually that was, in the first place, the best way to express this integral. Why is this integral easier to compute than this one? Well, let's see what it takes. Let's rewrite this, guys, here. The sum from 0 to 1 and the sum from 0 to x squared cosinus x third dy dx. You are first asked to compute an entire derivative of cosinus x third with respect not to x, but to y. So this is a constant of integration. So let me erase this integral, because I know that this integral I will never be able to compute this. But this one, I have some change. At least the first step, it's easy. Finding an entire derivative of cosinus x third with respect to y is nothing else than cosinus x third, cosinus of x third times y. And the first integral here, well, it simply consists of multiplying this constant by the size of the integral. Then you got x squared cosinus x third, and you sum from 0 to 1 dx. And now you can ask yourself, why is this integral now will be easier than this one? I still have a cosinus x third. Yes, but now with the change of variable, we should be able to fix this. So if you take u equal x third, you got du equal 3x squared dx, which is excellent because this is pretty much what I have up to a factor 3. So that is nothing else than, because of the factor third here, 1/3 times the sum from u equal 0, because when x equals 0, u equals 0, and when x is equal to 1, u is also equal to 1 indeed. So this is the same bound here. Cosinus u du. Well, okay, well this is now therefore very easy to compute. What is an entire derivative of cosinus u? Of course, sinus u, taken between 1 and 0, so the final result is sinus 1 divided by 3. I don't know what number sinus 1 is, I don't want to know, leave the result like that, that's perfectly fine. Alright, let's do the same thing for the other integral, the other one here. So I'm going to erase everything here. First of all, let's see what sort of domain we are considering when we write this integral. Alright, so it says the domain of integration with respect to y, that's the second step of integration. You integrate y between 0 and 1. Ah, okay, so now x equals 1, x equals 0, sorry, y equals 1 and y equals 0 are the upper bound and the lower bound of the integration. Alright? Now, choose y in between. And what are the bounds for x? The bounds for x is x equals 0, because of this guy, and x equals exponential of y. Ah, alright, so x equals exponential of y. Well, this is perfectly equivalent to say that y equals the log of x. So I have to draw the graph of y equal log of x, or x equal exponential of y. This is something like that, guys. And of course, the domain under consideration is everything here between x equals 0, y equals 1, x equals exponential of y, or y equals log of x, this is exactly the same, and y equals 0. This means probably that I could be able to invert the order of integration. Well, also I can tell you that this is definitely not a good idea to invert that order, because this integral will be easy to integrate versus the one I'm going to write down. But let's be curious and let's express this integral by just for the sake of knowing how to flip the order of integration. Okay, so now my integral, instead of having bounds with respect to y, I need to find bounds with respect to x. What is it? So the bounds with respect to x is going to be a bit tricky, actually. Yes. So the bounds for x varies from x equals 0. So I should not say that, x equals 0. And the upper bound, well, this is this value here. So when y equals 1, exponential of 1 equals x, so this is going to be e. So this is the lower bound for x, and the upper bound for x for if I want to express this integral over there, right? This integral by means of first an integration with respect to y and then an integration with respect to x. These are the upper bound. But you see, this is going to be the difficulty here. What are, once I fix x, what are going to be the bounds for y? X can be chosen here, and then in that case the bound for y will be 0 and 1, but x could be taken here. How are we going to do that? So it depends pretty much when x is before this point or after this point. What is this point? It's the point where y equal log of x intersect the x-axis. Well, this is x equal 1 precisely. So what I'm going to do, I'm going to find a lower bound like this. The lower bound, I claim, this is nothing else than what is the minimum value of 0. Sorry, what I'm saying here, it's, yes, 0. So it's not a mean, it's a max actually. It's a maximum value of 0, and what else? Well, the log of x. I need to explain you my thought. Let's look at this picture here, and let's don't put dots on the graph of the log of y of x. If I choose a value of x here, well, the lower bounds is definitively going to be 0. Well, it cannot be that value because the value here would be a negative value. So I'm just saying that the bounds for this integral will be the maximum value between 0 itself and the value that the log of x takes here. Yeah, it has to be 0 because log of x is negative. Now, on the contrary, if I take x after 1, the maximum value between 0 and log of x is log of x because the log of x will be positive. So that's why this should be the lower bound for the integral. And the upper bound is, of course, y equal 1, then nothing has changed here. And the integrand remains the same, but I need to integrate dy first and dx. Now finally, why? It is not necessarily very wise to do this. Well, for two reasons. Well, probably because here I would have to discuss whatever x is less than 1, x is more than 1. But it's not the hardest thing because I can split this integral into two parts indeed here. The sum from 0 to e and the sum from, let's say, so let's don't discuss this splitting now. Let's say so. This is definitively sufficiently well defined like that. But what I'm saying is that here, I'm requesting to find an antiderivative of square root of 1 plus exponential of y dy. I would have a hard time to find that again, an antiderivative of such a function. I can tell you in advance, you can use any form of substitution or integration by part and whatnot. You would have a hard time to find an antiderivative of such a function with respect to y. So forget about this integral, and probably you will never be able to compute it by hand. But this one, that's a little bit different here. So now I can erase everything here. Actually, I can erase also that formula, which was quite tough to end up with. So I wanted to express this integral into the sum of two integrals. It might not be a good idea to do it now. Let's don't give too much information on a single video. I don't think it's a good idea. Let's say here I claim that I'm capable to compute this integral. We are asked first of all to find an antiderivative of this bit, but with respect to x. So it's essentially the same idea as before. The square root of 1 plus exponential of y is a constant with respect to x. So the first bit here, that's very easy to do, is just this integral times the size of the interval. So it's exponential of y, because it's exponential of y minus 0, times 1 plus exponential of y. And then this is what we are asked to compute. Now you can ask, why suddenly this is easier than before? Well, because now we can use a change of variable. Exponential of y equal u, and you got du equal exponential of y dy, and exponential of dy is a PV. So this is nothing else than the sum from, okay, so when u equals 0, when y equals 0, u is equal to 1, so this is the lower bound, and when y equal 1, u equal e, and that's nice. And then we got square root of 1 plus u, so what did I say? Yeah, square root of 1 plus u du. And that integral, it's easy to compute because I know an entire derivative of 1 plus u. Actually, you know what? I'm not going to tell you. Instead of exponential of y, I'm going to take a 1 plus exponential of y. So in that case, this makes a 2 and a 1 plus e for the upper bound. And instead of having a square root of 1 plus u, I have square root of u. It's even easier. Well, the square root of u can be seen as u to the power 1/2. And therefore, using the general power rule, this is nothing else than u to the power 3 divided by 2 multiplied by 2/3. To be taken between 2 and 1 plus e. So this is 2/3 times 1 plus e to the power 3 divided by 2. Minus 2/3 times 2 to the power 3 divided by 2. And let's say we can leave the result like this. That's fair enough. So we will be doing these things. We will be taking an integral. It could be defined abstractly over a domain that we do not necessarily know clearly, that we do not necessarily visualize. But the thing first we need to do is visualize the domain on which the integral is given. Given abstractly with f of x, y, dA on a certain domain where the domain has a certain definition, or the domain is defined through the iterated integral, and then flip the order of integration. These are things that we're going to do a lot in the forthcoming videos.